With the dimensions of all the variables defined, we can move on to doing our dimensional analysis. And the idea of that is to plug in the dimensions of all of our variables into this equation and determine if the two sides of the equation have the same dimensions. Well, there's no point in me retyping this equation, and I'm just going to be replacing variables with dimensions. So I'm going to go ahead and make a copy of this equation. And I'm going to pop it right back into the document. But there's a little bit more reporting I want to do here in terms of saying what's going on in between these equations. Now, I'm not going to bore you in this video by you watching me type out this little bit of text. So I'm going to do a little copying and pasting from my notes here. And this is just a little bit of markdown that I wrote in order to describe what I'm doing. And I'm going to clean this up a little bit in terms of making sure that it's nice and narrow according to how I've been doing it in the previous paragraph. And in this case, I have more than one sentence. So this is an end of a sentence. I'm also getting to the end of the line, but regardless of whether I'm coming to the end, actually, you know what? I'm going to go ahead and do that. And I always put a new line after a sentence just so that it's easy to see where sentences start and stop. That's a little close to the end of the line for me, so I'm going to move that over here. And there's a little bit more math here in terms of what we're saying, but let's see what that looks like in our report. So I'm going to go ahead and preview. So we have the equation as we did before and the equation that we copied, and here's that new text. So checking for dimensional consistency in this equation requires substituting the dimensions of the individual variables into the equation. For the simplest perspective on dimensional consistency, we will assume that the integer 8 is a dimensionless ratio of 1. Now, sometimes you're presented with an equation where you're not really sure if a number in the equation has dimensions or not. If you've seen the derivation for the equation, then maybe you know something about where it came from and you know that. And I will tell you that for this particular equation, 8 is indeed a dimensionless ratio. But you can sometimes tell from the fact that it's an integer, especially a small integer. If it's an integer between like 1 and 10, there's a good chance that is coming from some sort of theory and it's a dimensionless ratio. But in this case, we're just going to have to assume it, and we'll see what happens with our dimensional analysis, whether that makes sense or not. Okay, so we have our equation, and what we want to do is substitute the variables in this equation for their dimensions. And that's going to get a little bit more complicated because the dimensions are kind of lengthy in terms of their LaTeX code. But let me go ahead and copy and paste the dimensions for bar u from up here and replace my bar u with those dimensions here. Also, I'm going to change this from being a square root to being an exponent of the 1/2. Just to keep myself consistent across my dimensions with using exponents, I'm going to get rid of the square root sign, and instead of being a square root, I need a left parentheses. So that's the open parentheses. And I need a close parentheses where I previously had the closing curly bracket for the square root. And that's the right parentheses or the closed parentheses. And then this whole thing is going to be raised to the 1/2 power. Now 1/2 is a fraction. So I'm going to raise this, and in the curly brackets for my exponent, I'm going to put a fraction. Again, that requires 2 sets of curly brackets. And I need a 1 in the numerator and a 2 in the denominator. So that fraction is the same thing as 1/2. And because I'm raising it to as an exponent, that means I'm taking this whole thing to the 1/2 power. Now, this fraction is going to get a little bit complicated because we have 4 different variables, all with their own dimensions in the numerator, but there's only 1 in the denominator. So again, I'm going to use the fact that white space doesn't matter or new lines don't matter and try to break this up in such a way that I can keep track of what's going on with this fraction. And one way I can do that, first of all, is to simply separate the numerator and the denominator. And I've separated the numerator and the denominator, but the numerator is still going to be kind of complicated. So I'm going to actually break out the numerator where each variable has its own line. So this is going to let me plug in the dimensions for each of these that I know get a little bit of complicated and put them on their own line, and hopefully keep it all straight so it's easy for me to see where different terms of this equation start and stop. Just to double check that I haven't broken anything, let's go ahead and do a preview on this and make sure it still makes sense. Now again, all that white space doesn't matter. So the stuff inside this fraction hasn't changed. I still have HGRS over F. But now you can see that I'm in parentheses, and notice how the parentheses with the slash left and the slash right have scaled to make sure they are big enough to accommodate this whole fraction that's inside the parentheses. That's why we use that backslash left and backslash right for the parentheses. And we have the 1/2 power in our exponent. So everything is looking good. We just need to finish substituting dimensions in for all of these variables. So I mentioned that the 8 we're going to think of as a dimensionless ratio. So I can copy the dimensions that I already have for 8, or for the number 8, in place of the 8. Then I can go back and find the dimensions for the acceleration of gravity. I can grab those and paste them in place of the g. I can go back and find the dimensions for the hydraulic radius. And in this case, I don't want everything. I'm just going to use, well, I'll go ahead and copy everything and paste it in. But I don't need both of these things in here. I don't need both the length squared over length and the length. I just need the length part of this. So I can get rid of this and the equal sign and just call that dimensions of length, because I've already done the work up here to show that it's derived from an area divided by a perimeter. And finally, same deal with S in the numerator. I can grab all of this, but I've already done the work to show that S is also a dimensionless ratio, a rise over run. So I don't need to show the length per length. I can just show a single dimensionless ratio. And then finally, we have the F in the denominator. And I already know that's dimensionless, so I'm just going to grab a dimensionless number from here and put it in place of the F. So if I haven't made any mistakes, I should be able to look at the preview of this and see a version of the Darcy-Weisbach equation with the dimensions plugged in for each of the variables. So the 8 is a dimensionless ratio. There's the acceleration of gravity. There's the hydraulic radius of a length. There's the dimensionless energy slope and the dimensionless friction factor. So that covers the first step of a dimensional analysis in terms of taking the dimensions of all the variables and plugging it into the equation that we're interested in.